PO4 -3 is phosphate, so we need 3 hydrogens to balance that out. Nitrous is NO2 because it's nitrite, has a -1 charge, so we need 1 hydrogen. Hydrofluoric, remember, if it's hydro, then there are no oxygens involved. Copper 2 hydroxide means that the charge of copper is 2, so we need 2 OHs because each one has a -1 charge. Phosphorus is phosphite, so that's PO3 with the -3. We need 3 hydrogens to get the 3 out. Carbonic is carbonate. So to do this, you have to look on here at carbonate. That's CO3, 2 negative. So we have CO3. Since it's 2 negative, that means we need 2 hydrogens to balance that out there. Going back to the naming. So here we don't have any oxygens, so we know that that's going to be sulfide. So we have hydro. Sulfide is sulfuric. For hydro and ic at the end for IDE. So sulfide becomes sulfuric. A little bit different. Here we have strontium and hydroxide. Strontium is in group 2A, so it does not need a Roman numeral. Strontium hydroxide. Cyanide. So that is cyanic. And since it's IDE, we put a hydro in front, hydrocyanic. K is potassium, it's in group 1A. So that is potassium hydroxide. Here we have Na and HCO3. That is sodium for Na. No Roman numeral needed. HCO3 is bicarbonate or hydrogen carbonate, either one acceptable. You'd only get that from looking at the periodic table unless you had that memorized. Ba is barium, it's in group 2A. So there's barium hydroxide. HClO, ClO is hypochlorite. So that will become hypochlorous. Hypochlorous acid. LiOH, that is lithium in group 1A. That is lithium hydroxide. H3PO3. PO3 is phosphite. So that is phosphorus acid. CuOH, that is copper hydroxide. Copper is not in group 1A, 2A, silver, zinc, or aluminum. So the charge of hydroxide is -1. So we only have 1 copper, so that is copper 1 hydroxide. Here, we have 2 hydroxides, so that's a total charge of -2. So this one would be copper 2 hydroxide. You need the Roman numeral because it's not in group 1A, 2A, silver, zinc, or aluminum. This one right here, very difficult. C2H3O2. Not the way we're used to seeing it. C2H3O2. Where are you? C2H3O2, right here. So that is acetate. Acetate ends in ATE. So that becomes acetic acid or acetic acid. Vinegar is 5% acetic acid by volume. So it's a low concentrated solution of acetic acid. That's what vinegar is. And that's what we got for the naming. All right. Questions about the naming? Normally we would have quizzes over that, but with this year, because everybody's taking stuff from home, you could look everything up on the internet, so there's no need to have a quiz on that. So just hopefully you guys go through that on your own. All right. Let's take a look at the Arrhenius acid and base concept. So an Arrhenius acid is any chemical that produces H3O plus hydronium ions, is what they're called, when dissolved in water. That's why we sit there and we looked at the chemicals above that had a hydrogen to start with, because when they dissociate, you get H plus H2O, which then yields H3O plus. That is the hydronium ion. A lot of times you'll see it that's just replaced with the hydrogen ion. That's fine. We can take these two things to mean the same exact thing. To calculate the pH of something, you take the negative log of the concentration. So if we take a look, negative log, let's say the concentration is 1 molar HCl. The negative log of 1 is 0. The pH for 1 molar HCl is as low as you can go. The pH scale basically goes from 0 up to 14. When you take the negative log, you get the pH, and that's basically the part hydrogen of it. Let's say that instead of having a pH or a concentration of 1, we diluted it so that it has a concentration of 0.1. Negative log, 0.1. That has a pH of 1. Negative log, 0.01. What do you think its pH will be? Two. Good, Lana. So then we take the negative log of 0.001. What do you think its pH will be? Three. We're going by a factor of 10 each time. That's basically what the pH scale allows you to do. It's the same thing if we take, for example, the negative log of 1 times 10 to the negative 2. The pH will be 2. Very cool there. Now, strong acids undergo what we call 100% ionization. Whatever their molarity is, that's their concentration. Whatever the concentration of the acid is, that's the concentration of the hydrogen ions. Sulfuric acid, if you recall, is H2SO4. So whatever the concentration of H2SO4 is, it will be greater, the concentration of H3O plus will be greater than the concentration of that, because sulfuric acid has the ability to ionize 2 hydrogens. So if we add this to water, we get H3O plus HSO4 negative. And we have another hydrogen that it can donate to another water to get another H3O. So that makes the amount of H3O plus more than whatever the concentration of that acid is. A weak acid only ionizes slightly. 1 molar HCl, you'll have 1 mole per liter of H3O plus. 1 molar acetic acid, you'll have much less than that, because the acetic acid does not tend to ionize very well. So the weak acid, we have to do this right here. We take the square root of the molarity of the acid times the concentration of the acid. That's not right. Let's do this. This seems to be changed to Ka. So the square root of Ka times Ca times the concentration of the acid. And Ka is known as the acid ionization constant. That's something that would be given to you. B, base. The Arrhenius concept of a base is anything that increases OH negative when dissolved in water. There is something called the POH that's not talked about a lot. It's the negative log of the hydroxide ion concentration. Just like strong acids, you get complete ionization. Strong bases, you get complete ionization. For such bases, whatever the concentration, for example, 1 molar sodium hydroxide equals 1 molar hydrogen or hydroxide ion concentration. Now, if it is a weak base, again, you have what's called the base ionization constant, Kb. So if we want to find the hydroxide ion concentration with a weak base, we take the square root of the Kb times the concentration of the base. The pH plus the POH always equals 14. That means that if the pH equals 7, that's right in the middle. The POH also equals 7. That's what we call pH balanced. So if we take a look here, these are the 4 formulas that we're going to be using. Water acts as what we call an amphoteric substance. It is both an acid and a base. The constant water, or what we call Kw, is the equilibrium constant of water. That equals 1 times 10 to the negative 14. That means water, pure water, has a hydrogen ion concentration of 1 times 10 to the negative 7 and a hydroxide ion concentration of 1 times 10 to the negative 7. What is the negative log of 1 times 10 to the negative 7? That would be 7. So the pH is 7 of water. The POH, or what's the negative log of the hydroxide ion concentration, or negative log of 1 times 10 to the negative 7? That would also be 7. So this is what we call the 4-corner diagram. Doing these math problems, this will be your guide for that. If you're given the hydrogen or hydronium ion concentration, both of these are the same thing, then you can get to either pH or OH negative. If you want to get to OH negative, you take the water constant, 1 times 10 to the negative 14th, and you divide it by this, taking the upward arrow to get this. If you want the pH, then you would take the negative log. If you have the pH, you can get to the hydrogen ion concentration by taking 10 to the negative pH, or what we call the antilog. That button is right here, 10 to the X. Basically, it's the opposite button of log. Or if you wanted the POH, you could take 14 minus the pH, and that would give you the POH. If you had the POH and you want to get the hydroxide ion concentration, you could go either up to the hydrogen ion concentration and over, or you could go over to POH and up. So this is very circular. So here is our work for tomorrow. We're going to do one of each of these problems right now, and then I'll give you guys the rest of the time to go from there. It says determine the pH if the hydroxide or hydrogen ion concentration is. Using our 4-corner diagram, we want the pH. So we need to take the negative log of these. So in order to do that, we have a calculator. We hit negative log, and then let's do 0.5. I'm going to do E. Negative log 0.5 gives me a pH of 0.30. What if I wanted to find the pOH of this? Then I could take 14 minus that answer. The pOH would be 13.6, 13.70. Right? And you can go all the way around that box for those. So here we have determine the pH of the hydroxide ion concentration is this. So the hydroxide ion concentration is 0.250. I'm starting up here. If I take the negative log of that, I will get pOH, and then I can subtract 14 minus the pOH and get the pH. Doing E here, negative log 0.25. 14 minus that equals 13.39 or 13.40. Determine the pOH if the hydroxide ion concentration is this. Well, as we said up there, the negative log of the hydroxide ion concentration equals the pOH. The negative log of 0.763, we get 0.117. So 0.12. Determine the pOH if the pH is this. Well, pOH equals 14 minus pH. So 14 minus 5. 14 minus 5 is 9. Determine if the solutions above are acidic or basic or neutral. We said a pH less than 7 is acidic. pH greater than 7 is basic. So for C, we have a pOH of 5 and a pH of 9. The pH is greater than 7, so it is a base. Determine the hydrogen ion concentration if the hydroxide concentration equals that. So H plus equals 1 times 10 to the negative 14th divided by the hydroxide ion concentration. 1 times 10 to the negative 12th. We're going to take 1 times 10 to the negative 14th divided by that. We get 1 times 10 to the negative second, or 0.01. Determine pH of the following and indicate whether the solution is acidic or basic. This time we're given all kinds of different things. This is the hydrogen ion concentration. So if I take the negative log of that, I will get 3. And that is less than 7. So that means if pH equals 3, that's an acid. Each one you've got to do something a little different. Determine the hydrogen ion concentration for the following. These are a little bit harder, but the pH is 8. So I take the 10 to the negative 8. Right? We take and do the antilog, which is 10 to the negative 8. Boom. 1 times 10 to the negative 8. Let's try this one. The pH is 7.2. We take 10 to the negative 7.2. So that is 6.31 times 10 to the negative 8. Last one, hydroxide ion concentration, given all these. So if I have the pH, I'm going to take 14 minus 8, and that will give me the pOH. 14 minus 8 is 6. That's the pOH. If I take 10 to the negative 6, that equals the hydroxide ion concentration. Depending on what you're given here, you've got to follow a slightly different path around the four-corner diagram. All right, that's all I got for today. I'll post the answers up there for tomorrow. You can check those, and then tomorrow's assignment will be the next page, right here, and right here. And what we're going to do on Friday is we're going to make an acid-base indicator, and we're going to test some common household products. Those in the laboratory will project that to you guys at home. That's all I got. If you have questions, by all means, stick around. Otherwise, you're more than welcome to go work on those problems. Have a great day.